All right, we're live. Let's do this. Shaders in beat. I'm gonna call it number 3, and I'm gonna say Ray marching, because we were at this point yesterday, and I'm so sorry. My whole microphone was off. So yeah. But it's good because we started a very long jam yesterday, and I feel like today we will, probably be a little bit more or less longer. Let's go to Shader Toy once again. So we couldn't review a little bit. We're going to make a review of the ray marching algorithm we started to see yesterday. So once again, let's say we have a ray starting at RO, going in RD in this direction. Say we have RD. Then we can query anywhere on this ray using the formula. Basically RO plus RD times T, where basically we say point T equals, right? So yeah, so meaning whatever we plug in T, it's gonna give us a line on give us a number on the line. So let's say we plug 1, then it's gonna be 1. It's gonna be 1, 2, 3, but you kind of get the idea. We went a bit deeper into this in the stream of yesterday, but tonight is all about making things in 3D. So we can review a little bit how the ray marching works. Let's define a simple. No, I don't want to put it. Let's put it in blue and green. I love green. Let's put a simple screen with a lot of pixels. So you have pixels and pixels all over. Then you get the idea. For every pixel, you throw a ray, starting at ray origin, and then you brute force-ish the 3D. Yeah, okay, it's going live. That's all good. So yeah, you kind of query the 3D world, and let me reopen that. So you start here, and let's say you have a sphere that is just sitting here in your scene. You want to find a point on this sphere. So let's say you have the ray going like this. This ray will never hit the sphere. So the way it works, we made this function called how far are we, or how close are we from the object in scene. So basically we call it the distance function, and sometimes you see D, simply DE. Sorry, I'm bad at writing. This function query the 3D space and returns from this starting point what is the closest object I am from. In this case, this would be the sphere. Then it returns the distance between this point and the sphere, meaning that you can walk on the ray this distance. Anyways, you kind of get the idea. I know it's a bit sloppy as example, but yeah. And eventually, if you have a ray, let's say you have a ray that goes super close of the object like this, well, eventually you're gonna hit the point. So you say, okay, if it's smaller than 0.01, then let's say we are in a sphere. So, as again, I love to open my Sublime text and make a little planning. So we're gonna make the ray marching algorithm in code, not explanation. We're gonna add a plane and a sphere, and we are going to mess around with 3D space. And yeah, what's cool? Probably I just want to show you the mod operator. They're very useful. And yeah, like, or maybe mod, and maybe at this point basic ray marching operators that we can use to combine to remove some pieces of shapes and so on. So to make the ray marching algorithm, once again, I'm going to go on GitHub and I will go on the page that is in the link in the description. If you go on my GitHub, just Google it. Yesterday we made, yeah, this is the code we wrote yesterday. I'm just gonna copy paste it because I kind of don't want to go on it all over again. So let's just copy paste that. And now we have the sphere. But yeah, let us just review a little bit how it works from what we explained in earlier session. We have the ray origin, which is where the eyes is kind of standing, where we're going to throw ray from to query 3D space. So we placed it at 0, 0, 0 and -4 on the z-axis. So have fun, load the code and mess around with. So example, if I say -12, then it's gonna query the 3D space, but the z, the RO, is gonna be, it's like if you look, the sphere hasn't moved, but the eyes kind of went all the way back. Just want to make sure that let me know if the audio is cool or not. I love to code with music, but yeah, maybe it's annoying. Because the thing is, with live stream, I'm not talking constantly. So I guess maybe I am. Anyways. So we can also, so let's say you have it 4 here. That would be the same thing. Let's just reopen Blender as we went yesterday. Kind of not really focus on the axis, but you know, you kind of get the idea. It's at 0, 0, and what we do is like we move it 4 scale on the right. We're not in the same axis, no naming, or damn, I can't move around. I'm sorry. Anyways, you get the idea. We just put the RO starting at -4 on the z-axis. We could change the x, so we could go something like 2. That would make the things move 2 on the right. And if we say -2, it would go 2 on the left. And guess what? You can also make it for the y. So -1, you could go 2, you know, it's kind of easy. Have fun, open the shaders, jam yourself in it. Oops, you have to be, yeah, -4. I'm gonna leave it at 0, 0 for now, because I just found it work pretty well. But there's also you remember this thing where in the first session we took the sine, which was the function going from -1 to 1, and we passed it the time so we would have very smooth things. Well, we can do this actually. We could say that we want to oscillate between -4, -5, and -3. So we could go sine of I time, and then if I hit the play button, so it's like if the camera would move, now it moves back, now it's gonna move in, and we query the sphere. We're gonna review this, no worries. I'm gonna comment this for now because I don't think it's very useful for now. Then I just define a basic ray direction. We saw this earlier, but take the UV, put the viewing direction to Z+. So example here, if I go -1, meaning we're looking backward, so I could just go and say 4, and then we're gonna have the sphere. So it's kind of it's like if we flipped the whole kind of, we flipped the direction. So, but I love to keep it Z+. Make more sense in my brain. By the way, the reason why like some software, they have Z from top, not Z, sorry, like in Revit, Autodesk Revit, or any CAD software, you have the Z axis, it points up, And in a lot of computer graphics, it points either like in the screen or back at you. And the reason why is because, well, that's just a little CJ facts here. Like a lot of software in CAD, like engineers and architects back in the days on those tables, they were drawing, looking to the plans like on drawing table. So it would make more sense for them to have kind of the z-axis in their direction. While computer science like us, like computer guys or computer graphics like us, what we were doing, we saw the z as we had the x and y is the screen, and the z is the depth in the screen. Yeah. Okay. Let's enough facts. Then we have color. I'm just saying it's right direction. We could have fun. Oh no. I don't like this. Oh, what's going on? What is going on here? Oh well, because I said, oh, we need to say 1 here. Okay, no, it's cool. So that's kind of the background color. Honestly, you could just leave it black. You could just say, I love to put RD because it kind of, it gives a nice kind of, yeah, just basically dynamic colors from wherever we are. So what sometimes you see is you go like rd.y, or yes, to make kind of a gradient, kind of a like sky-ish. You could play with the blue, but I'm gonna leave it to, for now, just RD, because why not? Then we define a current ray pulse, which is what we were talking here. Where do we start along the ray? We start at 0, 0, 0. It's normally we would start at ray origin, but you know, as we saw yesterday. Actually, I'm not even using this. I think I was really getting tired yesterday. So forget this. Current ray pause. Wipe this guy. We don't need this guy. Okay, and here is where we are walking along the ray. Sometimes you're going to see a function called trace. In some shaders, there's the trace function. Always put it in trace because it means like you're tracing along a ray and you want to find a hit point. But because we are implementing it from scratch and very going into the meat and very kind of to have a better understanding, I find it easier to learn it and to explore with ray marching concepts, having the kind of tracing loops inside the main functions. But it's actually the same thing. Not necessarily the same thing, but the idea doesn't change. So what we do here, we take 128 steps along the ray, and then we declare for every step, I've declared this underscore distance, and I'm calling this function, which is how close am I from the nearest object in scene, and I pass to it the ray origin that we've defined here. Then it's very ugly function name. How close am I from the nearest object in scene? I guess it's very ugly, but it still explained very well what it is doing. Then I check if the distance. Remember when I talked on here about if we get very close to a point on the sphere, then we say, okay, that's close enough. Or then it's this close enough, it's 0.01. So at 0.01, I just say, you know what, it's cool, you hit something. Now do some processing on, this is like the sphere, but it's going to do the same thing for every hit point. So if we had another cube and stuff, then it's all going to be related to this line of code. I've just put it in white for now. So we're going to have a material system probably tomorrow, probably, I don't know, sometimes from now. But I could change the color of the sphere. I could say whatever, something like RGB. So I could put it red like this, right? I could put the fract position. Fract is very useful when we create those kind of things. So if I go fract pos in this guy here, oops, fract arrow, yeah. So just to show you what fract does, it basically returns the the floating point, the decimal part of any float you give it. So let's say you have 1.25, it's going to return 0.25 and so on. It just wipes out the int part. Is this the proper definition? I'm not sure actually. Frac GLSL. Let's see what it gives. Compute the fractional part of the argument. Yeah, I guess it's, yeah. Compute the fractional part of the argument. Fair enough. Anyways. Let's put it back to white for now. Then we break the loop. And what we do is that basically we will redo the same thing for 128 times, but we don't want to start back at the origin because we were already there. So what we want to do is, okay, use the thing we define here. Let's use this function is the volume. Yeah. So let's use this function here. P of t is equal to RO plus RT times D. And what I do is I basically say RO, the ray origin, and I add to the ray origin the ray direction multiplied by the distance, which give us the new point that we had here. How close am I? You remember the algorithm. And eventually we get very close and we are on the sphere and we shade the sphere. We don't shade, we put it to white for now. The algorithm seems very, 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 very simple. Or the function, it's not even the algorithm, it's the function at this point. Takes in position. Then it's gonna we're gonna go into SDF today, because SDF Inigo Quiles, or let's take a look to SDF a little bit. I'm getting a bit away of the thing. Make the marching algorithm. I would say make/explain. This is kind of done. We kind of review it. We have it in code, so you can play with it. Then add a plane and a sphere. We already have a sphere, but before adding a plane and a sphere, we're going to go into covering, and I mean covering just a little bit of SDF, which means sign distance function. They are basically ways to represent geometry using using mathematical function that when you query them with a position in 3D space, they they return the distance from where you are, basically. So meaning, let's just open a brand new tab of, I need to get a new software, honestly. I'm sorry. A lot of people, they cringe when they see I use Paint, but I love Paint. So let's say we have the SDF. Here is our beautiful sphere. Make it 3D, so... Okay, so the SDF mean that you have a 3D pose. 3D pose. Okay, vectory. And the SDF, it takes this point and it returns a value that is greater than 0 when you're out of the shape. So like maybe here you're like at 12 meters from the sphere. So it returns 12. If you got very, very, very close here, probably you're at like half a meter, 1/4 of a meter. And then eventually, if you're exactly on the sphere at this point, it's return 0. And if you're inside, it returns positive value. So let's say we have a radius of like 2 meters. It's going to return here if you're inside at the total center, 1 meter plus 1. Greater than 0 and, smaller than 0. I'm sorry, greater, yeah. Is that it? I always get mixed around, yeah. Anyways, you kind of get the idea. Yeah, this is it. So basically, this point returns the distance, and as you move away from the shapes, the distance from the SDF you call using the map function we implemented gets bigger, right? and if you're inside, it's negative. Then we defined the sphere SDF. If you are willing to take a look to deeply understand how, oh no, I don't want to. Okay, if you want to take a look to how the SDF shapes very work, I recommend to you the Art of Code, which is an excellent show. I say show because it's an awesome YouTube channel, and he made a ray marching. Where is it? Is it? No, very simple shape. Where he goes and he explains very well all the SDFs and how they're done. So go to see this to have a better understanding on how they works, because honestly, like, I don't want to cover them all because I just think it's nice to understand how they work, and you need to understand how they work and how they're built. But it's, I guess once you learn them and you work the math with Martijn here, his name is Martijn, you're going to be good to go. And after this, you always get back to the Inigo Quiles, which is the founder of Shader Toy. He made this article that is primitives. And what you do, you always go here, copy paste, and then you add them to your SD to your code, and it just works. That's part of the life of writing SDF based ray marched shader. So sphere, it's cool. We talked a bit about SDF. Let me just go here. SDF. Like, we simply covered the 0.001% of what are SDF, but you kind of get the idea. They are mathematical way to represent 3D object. So then you can query 3D space and see from a point, are you near, are you far? Very useful things in ray marching. Then we're going to add a sphere. It's already done. We had the sphere. Oh, let me just show you something. With sphere, we have two arguments, a position and a radius. And I think at this point, what is very useful is we take a look to how close am I from the nearest object in a scene. We pass it a position, and then it returns the sphere. We pass the position and the radius. So if I scale the radius by, instead of 1, I say 2, or instead of 1, I pass it 1.5. Well, guess what? The radius is growing. So what about making it grow on like this, right? So now it's going to go bigger, then it's going to reach to 0, it's going to go back, and so on. Yeah, you can do this. This is just changing the radius of the sphere. Another thing you can do is to take the position and say that is a very useful thing with ray marching, is because you query the 3D space using SDF, you can simply change from where you query. Now what we passed was where we were along the ray, but nothing is bad to say, okay, instead of like our sphere to query from the position we are, let's add another vector tree and change the X, the Y, and the Z. So if I put 0, 1, 1, and 0, then you can see that the position of the sphere has moved. Well, it's not a position of the sphere, it's like the whole space. We kind of move 1 unit on the X. 2 unit, 3, 4, 1, 0. You can do them on all these. You kind of get the idea. I guess at this point, I'm gonna go and copy paste this. Let's write 2 little name for, I'm just going to drop the volume a little bit. Okay. So let me just define a vector tree. I'm going to call it sphere position, and I'm just going to copy paste this guy over here. Well, I just could say this sphere pose offset. I guess it makes a bit more sense. So now I could simply add this guy here, sphere offset. And then I'm gonna define a float radius, which is gonna be equal to 1. There we go, there we go, there we go. All right, we're good to go. We have the sphere. Now we need to add the plane. So we need to make a new function called plane that's gonna take a vector tree. It's gonna be the position, and it's simply going to return the position of y. Is that it? Let me just go on once again. You have the camera, you have the floor, it returns the distance of y. So sorry. Having a bit of 7-Up. live stream fun. Okay, let's do this. So now I could just say now we need a very so if you take a look to the code, how close am I from the nearest object in the scene? We have the sphere, and then we basically we just return the sphere. Well, we need to create more objects. So and objects are basically where we are. This where the nearest objects are. But now if we only have a sphere, it's cool. We could just return sphere, but eventually you could have a sphere, cube, house. You could build the world using those 2 triangles. So I'm gonna say distance 1 and pass it this guy over here, which it's gonna do the same thing. Okay, what I do here is basically what I'm doing is say, okay, let's keep track of the distance of the sphere in distance 1. Because after this, what I could do is add more, kind of more. So, and it's kind of counterintuitive to think about object and distance, but in remarching, you get used to it. Like this is distance 1, but I could say like sphere, right? And that would work too. Sphere distance, if that makes sense. Sphere distance. Now what we want, because remember this guy, what it does is query 3D space and it just returns the nearest distance of where we are. And if we're close enough of the object, then we are on it, and we can process the color and stuff in the color loop in here. Oh. Now I'm gonna add plane, float plane, and say something like I'm just gonna go and query the plane function we just have written. I'm gonna pass it sphere distance, not sphere distance. If I pass it plane in here, if I return plane, I should have the plane. Oh, I don't have the plane. Mine, what's going on here? Oh, that's because we're like flat, so we need to put it a bit up. That is something that's always gonna be like if you put the camera like 0 on the floor, and you kind of query to know where is the floor. Well, you're on it, so it's always gonna be 0 from this, like because it returns a position dot y. So here's the trick. If we have the floor and our camera or RO is there, you know, like we're basically on the floor, right? So we're asking, how close are we from the floor? How close are we from the floor? How close are we from the floor? And the guy kind of turns nut, the algorithm kind of turns nut. It say, well, yeah, you're on the floor. You're at 0, you're on it. And because here we query 0.01, well, it's smaller because we are on, we're like on it, on the floor. Yeah. So always simple things. Always put your y a bit up, or the axis, the vertical axis a bit up, it helps and it will resolve some bug. So now we have the radius. We could just return the radius. Then we could, oh, not the radius, the sphere. Distance. I'm getting a bit lost in my in my naming. Yeah, maybe 2 is a bit too much. I say 1, and even place it back, or yeah, -1, -2, -5. That is something you well, you know what? Let's add -1 here. Now we're good to go. Okay. Yeah, kind of. Yeah, that is something that happens all the time. So you're going to mess around with the, like, where the ray starts, how you manipulate objects. So yeah, have fun and hack around with it. So plane. So we have the sphere and we have the plane. Now the question is, how do we combine both? How can we make sure that this thing is, how close am I from the object? Well, it can return and the floor and the sphere. And to do this, what we do is we use the min operator, which always going to return the minimum value. So meaning if we need to collide on the, because every 1 pixel only got 1 hit. So if we hit on the sphere, we hit on the sphere. If we hit on the plane, we hit on the floor, we hit on the floor. But if we are in a place where we could hit one or the other, we simply return out what's the first one, what's the minimum. So if I say plane and I go sphere distance in here, then we have both and we can start to shade them. Okay, let me mess around with 3D space. Oof, was a bit heavy. Plane is done. Plane is done. Now, oh God, I'm sorry. Didn't. It's Thursday night. Now we had the plane. Plane is done. Plane is just perfectly done. Mess around with 3D space. Well, this I'm gonna put almost done, because like what I mean by mess with 3D space was what we did here with the sphere. Really, was to kind of move it around. We can even kind of add some sign of high time on the X, on the Y, you know, and then if we hit play, you're gonna see it move onto the floor, going up. It's very ugly because for now everything is white and we need to shade a little bit. So we're going to shade. Do we shade tonight? Here's the question. It's already midnight and we are at 27 minutes. And I feel, no, we're at 33 minutes actually. So yes. Do we shade? Do we start shading? That's the question I'm asking. You know what? Yeah. I wanted to go into basic ray marking operators, mod. Yeah, let's go a bit with mod. Okay. I have to say, yesterday I kind of wrote down where I wanted to go and it helped. And tonight I just opened the live stream and went in. So I guess we're not going to go into shading because I know myself, if I dive into how to generate normals without normals and using the hack everyone is doing, there are a good chance we're going to go for another hour, and I'm not sure I want to do this to myself because I'm getting very tired. Yeah, so let's maybe add a rotation on the X. And then the sphere is gonna turn. I don't want to shade, but still I want to make just a little bit more dynamics. So what I could do is, if I go, and let me try something real quick. If I go and I go vector L is equal, and I'm gonna like vec LP, like without normals, I'm not sure it's gonna work. Actually, I'm quite sure it won't work, but and two up and -5 back. What if I then say okay, I'm going a bit out of explanation here, but yeah, because I have it in my head, so I'm sorry. Distance more point shade minus LP, so I could go what gives us, yeah, and then we cross it, so. Dot LP and P shade. What do we distance minus RO, ray origin. Okay, ray origin. LP P shade. I'm gonna convert IP, so victory. And let's give it a try. If I got a shaded. Oh, I'm so not sure. I don't think it had worked actually. Maybe switch those two around. Okay. No, really, it. Oh, I need to maybe if I normalize. Okay, now I'm going completely crazy. I'm sorry. Okay, yeah, we're gonna say now it. Okay. Yeah, this is not a lighting. Don't take this. This is just because we don't have normals. This is fucking disgusting. I can add a bit of like 0.5 to it just to make it less ugly. Okay, now, but anyways, you kind of see the idea where now the sphere is moving because we changed position offset. And there's the mod operator. I'm gonna open another shader I have because okay. By the way, I'm sorry if what I've been done here is completely ugly. It is for me, no worries. And I just kind of try to fake a lighting thing just to give a bit of depth, because I don't love to say, okay, here's frag. So yeah, it's not very lighting. I mean, it's not lighting, it's disgusting. It's the ugliest pieces of shaders I've ever seen in my whole life, to be honest with you. But at least this is this is ugly. But the good news is that we are going to tomorrow implement Lambertian lighting. Tomorrow is Friday night. Maybe not tomorrow, but in the next one, we're going to go into shading, calculating normals, and start to put lights to our scene. Because now we have a sphere, we have a plane, and we have the list of all the SDF we can add. So, go to see this guy. He's very good, Martine, by the way. I feel like the live of tonight is very chaotic, and what was I talking about? Mod operator. Sorry. Okay, so I'm just gonna show you because sometimes you're gonna use it a lot. The mod operator, so I could go sphere repeat. I have it, basic repetition. So now there's a way you can actually query, and you see here it repeats the sphere infinitely. So let's implement this in our what you're gonna do is we're gonna use the mod operator, which basically gonna take the space and reset it to 0. Is that the good way to explain? Oh, I started the stream very, very late. I'm so sorry. So, mod GLSL. Let's open the documentation. What this guy do? So, unable to use. Yeah, that's it. That's the thread I'm. That's the thread. Yeah. That's the thread you're always gonna fall in. I'm gonna add it to the show note. Can I hit it? Can I hit it? I'm not sure. Let me just. I'm gonna go there. And I'm also gonna add the Martin one. Anyways, we could dive like how it actually works in later sessions, but I think that for now what I'm gonna go is just to show you how it is used, and you can even, you know what, have fun and use it yourself to kind of see how it works. So basically the way it works is we define repetitions over a domain and we put it back to 0. This is not work. Yeah, it's, yeah. I have to say episode 3 is by far the more chaotic one. 125 plus modulus. Where do we... What's going on here? Oh, maybe here? Okay, yeah. Yeah. I'm just gonna leave it to position, and okay, now. Like a 0.15 maybe. I don't know what's going on. 0.3. Oh, okay. It's on the X. That's the problem. So I'm gonna put 2 here. I'm gonna go 4. So you kind of double the space to grow, and then you remove back 2. And I'm gonna do for Z. I'm gonna basically do the same thing. 2, 4 minus 2. I could go 3, 6. But yeah, doesn't seem to work. Oh, 0.12. If I put 1, what do we have here? Okay, now we can see that the sphere kind of repeats. We have definitely depth problem. I could go and make them move. Time vector maybe up and down on the Y. Oh, not pause. I time. Okay, now we can see that they are... Oh, okay, now we see it. Cool. Okay. Oh, I kind of see it. It's because we need to add a bit more. -1 here. And now we have all the spheres. It's not very talking because we are... Put it from maybe 4 or 3 or 2. Anyways, you kind of see that the sphere repeats. We could make it... It's very ugly because we don't have the shading. So you know what I'm gonna do? I'm gonna wish you a very good night. I hope you had a good time watching. And there's gonna be more. I love the stream. I kind of enjoy. Oh, there's someone in the chat talking. Oh my god, I'm so sorry. Kartik Karan say how to anti-alias. Oh, there was someone watching. I'm so sorry, Kartik Karan. Am I pronouncing it right? There's someone in the live chat. Okay, this is so exciting. Auto hentai alias. Okay. To hentai alias, you either send more ray from one, or you there's many ways in ray marching to hentai alias. To be honest with you, I would need to review a bit how we do this, because I know you can multi-sample along a hit point and kind of blur the result of the hit point, but I'm not sure it's the way it's done. So you know what? Oh my god, I need to check the chat. Was someone in the chat. Guys, I'm so sorry. This thing is the first time that ever happened. Someone's writing to me on YouTube while I'm streaming. Anyways, yeah, excited. Woo, fireworks effect. I'm gonna, and I can't believe, I mean, this is so lame. Like, some people, they have like, how do you do? They have like 100,000 people watching them, and they talk about shaders, and I'm like, I'm getting super excited because there's one person in the chat talking. Anyways, Kartik Karan, thanks for watching. I'm going to make, that's a good idea. We're going to go into alias later. You know, this is a story of a long journey. We're going to go every day, every week, and write shaders together. And the thing about it is I don't take myself really serious about this. I'm far from being a pro in shaders. I'm far from being someone who knows everything. And I'm just a nerdy guy that somehow, for some reason, have fun talking to YouTube. And I bought myself a microphone, so I love to test it while doing live stream. That being said, as always, the code will be this code. Let's remove this, because for now it's kind of just messy. I'm gonna leave it, but as always, the code is gonna be on the GitHub, and I invite you to simply download it and have fun with it. The lighting is completely disgusting, but yeah, tomorrow we're gonna go to Lembertian shading. Then what we're going to do tomorrow? Lembertian shading, calculating normal is gonna be a good subject. We could dive for hours into it. And how do we handle normal in a place where we don't have normal maps and stuff? Actually, the code is only 6. That's an interesting subject about calculating normals in array marching, is that the code is only like 6 or 7 lines of codes, but the technique is so beautifully and have so many fields that we could explore. And so, yeah. Whatsoever. Join in the next one, and until then, I wish you a good night. Have a good night sleeping. And the code of the shader, once again, that's what I wanted to end for, is going to be available on the GitHub. And I'm going to just paste it. By the way, let me know if, because I'm feeling that this file is going to grow very big, very quick. So maybe I'm going to put like all the live stream 1, live stream 2, and so on. So we could have more, we could have a bit more, bit more control. Anyways, thanks a lot for watching. Have a good night. And I wish you to all to have a good time writing Ray Marcher and think about SDF.